Hello, my fine feathered friend. Hello, can't talk anymore. Hello, my fine feathered friends. We are continuing part two of section 3.1. Here we go. Let me switch cameras. I'm going to a little thingy thing. There you go. Alrighty. So we had learned in part one of 3.1 that the we talk about the area under the curve. So we call this the integral from a to b of f of x dx. And now I might have mentioned that the dx is just something you write, but it's more than just something you write. The dx kind of represents, remember we had split this into little tall rectangles. The f of x kind of represents the height of each little rectangle, and the dx kind of represents the width of each of these little rectangles. And why am I saying kind of represents? Because the dx becomes infinitesimally small. So it's a very teensy. I have another question I want to ponder at the moment. So this is we said the area under the curve and under the curve, to the x-axis, right? What if I have what if this is my, that's my y and that's my x, right? What if my curve is down here? So that's A and that's B. So what's the area under the curve? Well, it's really not the area under the curve. It's the area from the curve to the x-axis. So really, is this area. The only thing is, if you remember, let's say, for example, we break this into rectangles, right? So this rectangle over here, we said that the height we represented by the function value. So f of let's say that, and I'm just picking a random point here, right? So f of we'll call that c, some random point c. So f of c is like, I don't know, -5. And the width, let's say the width is 0.1. Let's say the delta x is 0.1. So the area of this rectangle is -0.5. So, how can a rectangle have a negative area? It just doesn't make sense. It's an object here, I mean, look, I'm looking at this. This is if I'm gonna carpet this or paint this, and I go into the carpeting store and I'm gonna say, hey, I'd like to buy -0.5 square feet of carpet. It'll be, huh? What are you talking about? Well, that's the difference. It's one of the differences between calculus and, let's say, like geometry. As far as the geometric figure is concerned, the geometry of this, yeah, this area down here is a positive area. But in calculus, the area under the curve, we call it a negative area. And we have that concept, we have the concept. This is the difference really between the integral and the actual physical area. Just like if you guys ever learn like physics, right? The difference of speed versus velocity. What's the difference? Well, if a car is going backwards at 90 miles an hour, the speed is 90. The velocity is -90. Because it's going backwards, the velocity is -90, but the speed is still 90. Look, if that car hits you, it's still going to hurt. It's going to hurt just as bad as a car going forward at 90 miles an hour. So that's the way it is in calculus. When it's under the curve, we talk about it being a negative area. Another thing we would say, just to give an idea how of how calculus works here, is that if I'm looking at the integral, let's go back to my case of a curve that's above the axis, for example. So that's A and that's B. I'm looking at the integral from A to B of f of x dx. That's y equals f of x, and we're all good. And let's say this equals, I don't know, 10. Let's say this area under the curve. Let's say the integral is, it's, I don't know, let's say it comes out to be 10. I don't know, I'm just making up numbers here. Let's say it's 10. Well, if I would do this, the integral from B to A, meaning reverse the direction. So instead of going from A to B, I'm going from B to A. Then I'm going to say it's -10. Again, we're talking about a directed area. And it's you know, and that's the difference between, like I say, if this was pure geometry, then area is area, and that's it. Area is area. But if we're talking about a directed area, in calculus, we're talking about a directed area. Um, that's what integrals are. Integral is really a directed area. Now, let me give you another example. If I would talk, oh, look at this. If I would talk about, oops, suppose that so if that's A and that's B, so the integral from A to B, it's really going to be, this area here minus that area there. And the integral, let's say again, this is f of x. The integral of f of x dx, it could actually wind up being 0, because it could be that this area is the same as this geometric area is the same as that geometric area, and the two kind of cancel each other out. In fact, if I had a function, let's say I'm going to make an exact function now. Okay, y equals um 1 minus x. Y equals 1 minus x. So if I graph it, looks like that. So that's 0, and that's 1, and that's 2. Well, clearly we see from the geometry that that's the area of the triangle with 1. Height is 1. That's 1, by the way. This triangle has a base of 1 and a height of 1. Again, geometrically. So these two areas, so that means that the integral from 0, x is going from 0 to 2 of f of x dx. In this case, where f of x is equal to 1 minus x. So there is the integral from 0 to 2 of 1 minus x. That's my f of x function, dx. It's actually going to equal 0. Now, does that mean that if I would ask you how much paint do you need to paint that, you need no paint? If I ask you how much carpeting do you need to carpet that, you didn't need no carpet? No. The physical area exists. The physical area is whatever it is. But the integral is not necessarily the physical area. Now, I might give you a question. I might give you a question. What is the area of these? How much paint do you need? And then we'd have to do it. We have to do the problem differently. What we'd actually have to do is to break. And this is what we would do. We would say in this case right here, we'd say, let me just move my thing here. So we would say the integral from 0 to 2 of 1 minus x dx is equal to the integral from 0 to 1 of 1 minus x dx. And that's this part right here. And then I have to break it up into the integral from 1 to 2, which is that part down there, of 1 minus x dx. But again, that's going to be, well, let's see. This area is going to be, well, it's 1 times, this area is 1/2. That area is negative 1/2. So I know it's 1/2, and then plus negative 1/2. And and that and that of course equals 0. So what I'm going to do here, there's two ways you can write this. If I want to know the actual area, how much carpeting am I going to need, to carpet this. So I could write this. I could write this. I have to write like this. I'm going to write that it's equal to the integral from 0 to 1 of 1 minus x dx. Yeah, that's cool. Minus the integral from 1 to 2 of 1 minus x dx. Because this way it's 1/2 minus negative 1/2. And then you get that's just the area is 1, which is what that total area actually is. Another way of expressing the same idea is that you could say that area, the actual area, I'm gonna write actual area, or I can say carpeted area, what if I say? I could rewrite it, but I could say it's the absolute value of the integral from 0 to 1 of f of 1 minus x dx plus the absolute value of the integral from 1 to 2 of 1 minus x dx. Because then I get, this is just the absolute value of 1/2 plus the absolute value of negative 1/2. And that also comes out to be 1, which is what it's supposed to be. So that's I just want to give you some differences between calculus and let's say like geometry. If this was a geometry class, we wouldn't even be talking about negative areas, things like that. But it's not geometry, it's calculus, it's different, and we're talking about, I guess, the concept that we're saying here is the concept of what we would call directed area. So for example, let's say I have a curve here, y equals f of x. And it goes like this, and it goes like that, and it goes like this. Let's say that's a 0, I don't know, 1, 2, 3, 4, 5, and 6. And let's say that the carpeted area here, the carpeted area is 2. And the carpeted area here is, I don't know, negative 5. Let's say it's negative 5. Let's say it's 5, I mean. The actual carpeted area. Or if I was laying down carpeting and painting, the area is 5. And here the area is, I don't know, here the area is, I don't know, let's say it's also 2. This little section right here. So, and this is of course the curve y equals f of x. It's important to know. So the integral from 0 to 2 of f of x dx, in this case, is equal to 2. The integral from 2 to 4 of f of x dx, in this case, is negative 5. Even though I said it takes 5 square feet of carpeting to carpet it, but it's below the x-axis, so the integral is negative 5. The integral of this guy here from 4 to 6 of f of x dx is equal to positive 2. How about the integral from 2 to 6? What's the integral from 2 to 6? Well, I have the 5 and I have the 2. That's a negative 5. It's going to be negative 5 plus 2. And that's going to wind up being negative 3. So the integral, how about the whole shebang? The integral from 0 to 5 of f of x dx, well, that's going to be 2 minus 5 plus 2, which is equal to negative 1. So the integral, so again, the area, like I said, the area, if I'm painting it, the area is the total painting area is 9. I mean, it's 2, 5, and 7, 2, 5, and 2, it's 9. But the integral is not quite the same thing as there. We talk about the integrals being the quote area under the curve, but it's not quite just area under the curve. I want to show you 2 interesting things that are in the textbook. These are business applications, so I'm just going to show you straight from the textbook pages, kind of It's kind of again an application of integrals. So let me switch cameras here. Let's see. I'm going to switch. Again, this is from a textbook. Suppose that the MR, that's the marginal revenue, of of selling Q dollars. That's marginal revenue is dollars per item. Selling Q dollar. Anyway, oh boy, I'm saying this so badly. MR of Q is the marginal revenue in dollars per item for selling Q items. There you go. It's much easier to say it just the way it's written right there. What does the integral from 0 to 150 of MRQ dQ represent? We're not asking to calculate anything. We're just asking what does it represent? And the answer is it represents something called accumulated. The integral, first of all, the units, MRQ is dollars per item, and DQ, that's items. So dollars per item times item is just dollars. And the integral represents the accumulated dollars for selling 0 to 150 items. That's how many dollars you accumulate in that interval. So the integral from 0 to 150 of MRQ dQ is equal to TR 150, which is the total revenue from selling 150 items. That's what it is in this case. I thought it was kind of interesting. There's another case that the textbook has. Let's take a look at it. Number 7. Oops, where'd it go? Just a second ago. What happened to it? Where is it? Let's find this. So suppose R of T in centimeters per year represents how the diameter of a tree changes with time. So what does the integral from T1 to T2 of R of T dt represent? T1 and T2, everyone knows that's Terminator 1 and Terminator 2, if you're Terminator fans. Otherwise, I guess it means time 1 from time 1 to time 2. So in other words, in between, in that interval between two different times. Anyway, what does this represent? So the integral, so first of all, the integral from T1 to T2 of R of T dt, the unit has units of centimeters per year, because that's what we said, that's what R of T is the units. And dt is time, so it's just, it's years. And centimeters per year times the number of years, that tells you centimeters, that's centimeters. And so therefore the integral represents the accumulated growth of the tree's diameter from T1 to T2. So the integral from T1 to T2 of R of T dt is the change in the diameter of the tree over this period of time. That's really interesting. I want to show you one more pretty important thing here. So I'm going to switch cameras again. Here we go. Just want to show you very simply. Okay, here we go. If I have the integral suppose I have the integral from, it doesn't matter, a to b of f of x dx. Let's say that equals, I don't know, 17 square inches. Here's the graph of it. That's A and that's B, and it looks like that. And this area down here is 17. Well, if I would have the integral from a to b of 2f of x, well, so this here is y equals f of x. If I would have y equals 2f of x, what happens is that it doubles every value. So this everything will become double. So it would look, so 2f of x will look something like this. And basically each rectangle, the rectangle that went here, this rectangle which had a height this high, is now going to have a height twice as high. width is not changing, but the height is changing. So like if I pick that rectangle over there, that's f of x, and that's 2 times f of x. That's y equals 2 f of x. So basically I have all these rectangles which are double the, so it's the same rectangle. So just like I added up all these rectangles here, I'm adding up the same number of rectangles, and the rectangles have the same width, but each rectangle is double the height because 2 f of x is just double whatever f of x was, which means that this is just going to be 2 times 17. This is going to be 34. Because if I add up these these rectangles which are shorter, and it comes up to 17, and now I add up these entire long rectangles which are twice the height, then the area is going to be double. And that leads us to a very important rule of integrals, which comes up a lot, which is that the integral from a to b of k can be any constant. It doesn't have to necessarily be 2. It could be any constant times f of x. That's just going to be k times the integral from a to b of plane f of x. In other words, this here is the original rectangles. This is the rectangles that are multiplied. Here I have each rectangle is multiplied by k, and here I'm just taking the total of all the rectangles, just taking the whole smack and multiplying it by k, like as a group, if you will. So it winds up being the same thing. This is quite a interesting and important rule, and it's something we're gonna make some of that's very useful. This is a gem. I'm giving you a gem here. Well, everybody, that's it for this video, and it's been lovely and fascinating as always, and I will see you all next time. Bye.